All right, thank you, Martin, for the introduction. Can everyone hear me in the back? Okay, if not, if I quiet down or something, then just wave and shout. Yeah, thanks for the introduction and thanks for the invitation to talk here today. I think it's been a great morning sessions already, so really looking forward to the afternoon. And yeah, as Martin introduced already, I'm going to talk about well, from big data to big knowledge. I'm only going to talk about maybe the second half of the talk actually about Google-specific work. And before, I just want to take a high-level kind of step back and see, where are we in that field and what's going on and why is there all this hype around it and what does it mean for us and for developments which are going on. So first of all, what is big data? And there has been this definition on the World Congress of the Economic Society, Econometric Society. Big data refers to the explosion in quantity and sometimes quality of available and potentially relevant data, largely the result of recent and unprecedented advancements in data recording and storage technology. Okay, sounds like a fairly dry but somehow fitting definition. Interesting here is already potentially relevant, because that's one of the key things which is not always given with big data. And secondly, it's also a hype. Not necessarily in a bad sense, but it's really one of those buzzwords. I was kind of ashamed to put it in the title, but hopefully it will make sense for the talk. So the fact that it is a hype can actually be seen if you look on Google search trends. So you probably, maybe some of you know this site. If you just go on google.com/trends/explore, you can see the trends of a search term or multiple search terms in conjunction. And if you just look for big data, then you see that there's really this, well, more or less linear ramp up since 2012, where a lot of queries are actually coming in for big data. So it is a hype. The question is, why is it actually a hype now? Because it's not a new phenomenon. So in the 40s already, 1940s, a librarian estimated that American university libraries doubled in size every 16 years. And by that extrapolation, Yale would have kind of exploded, or would explode, in 2040 with 200 million books occupying 6,000 miles of shelves. Back then, without computers, but that was the estimate. And then in the 60s, there was a similar realization that data grows exponentially. So Derek Price published a paper where he estimated that the number of observed that the number of scientific publications grows exponentially. And he attributed this to basically one scientific discovery unlocking n new discoveries. And so you basically have this exponential growth rate then. And then in the 70s, 80s, and 90s, there were similar observations. Every now and then a paper which claims, yeah, we have exponential data growth, and at some point we are going to be overwhelmed, and what do we do with the data? And this is from Martin Hilbert and Priscilla Lopez in a science paper 2011. That's an estimate of the world's storage capacity. It's a logarithmic scale, so you can see that over the past 30 years, essentially, the storage capacity has been growing exponentially. And note also that between 2004, 5-ish or so, there's a shift, a gradual shift from analog data or analog media in orange to blue digital media in blue, which means easier distributability, and it's easier to copy data and to analyze data, all that stuff. So, but you can also see here's the same trend. The data which we can store and which we do store is growing exponentially. So again, why is it such a big hype now? And in order to think about that, we need to go back to the what again. So what is big data? And it's actually really useless if you can't do anything with it. If you think about like millions of phone books or something, that is data, that's big data, but no one would ever read them, and so there's no real use in them. And we only really get information out of big data if we combine it with advanced algorithms that allow us to extract patterns, detect features which, as a human, we might not immediately see, or even just to index big data, right? So all these things are actually technologies which are becoming or which have become available in the recent years at this scale, which we need to really process big data. So search and indexing, for instance, I mean, we have Google search, we have Bing search, and those search algorithms are way superior than what we had, back in the, late 90s, let's say, with Alta Vista and Fireball and everything. But even those were already very good at indexing what formerly wasn't even possible to index to search. Secondly, we have algorithmic advances. And that's specifically important for deep learning and other things I'm going to talk about later. But you can basically imagine that beyond search and indexing, you also want to understand emerging patterns, underlying structures in the data. And that's only possible with really advanced algorithms. In order to execute these algorithms and also to build them and iterate the model, you need processing power. And since the early 2000s, GPUs have become much more inexpensive. So we have another resource of processing power via GPUs, and that enables advanced algorithms, and that facilitates big data analysis. Next point, mechanical Turk. And I think this is often overlooked when people think about what really enables this maybe breakthrough point which we are right now. Mechanical Turk is you probably all know it. It's an Amazon technology where you can send out questions to basically operators for you who answer them. It can be like labeling questions, it can be translation questions, it can be basically anything. And the purpose of this is usually to generate ground truth. And in order to build advanced algorithms like deep learning networks, you usually need a large amount of training data. So that's where Mechanical Turk and other technologies we capture come into play. And then you also need infrastructure and bandwidth, not only to actually run the whole computation and everything, but also to serve Mechanical Turk and other things to users or operators in the world who actually do this for a cost which is feasible. Think of emerging markets, where a lot of people actually earn their living through micro-tasks like that stuff, or at least have a significant portion of the income. So and without the internet and the infrastructure to actually serve the data at fairly large bandwidth, in particular if it includes image data, that wouldn't be feasible either. And then lastly, we now have an economic or an ecosystem of applications which drive progress. We have cell phones which have location awareness. We are basically online all the time. You can just walk through the city and make some query, where's the next cafe, where's the next restaurant, and you expect to get an answer. Same with navigation. You want to know where the traffic is, you want to avoid traffic jams. We are developing self-driving cars, all these technologies which really rely on intelligent algorithms to act and interact with the real world. And I think this is one of the key drivers also for technology breakthroughs nowadays, that there needs to be an application. And yeah, all of this is actually coming together now, if you think about it. Most of this is actually fairly recent in the last decade. And that is really, I think, what enabled many breakthrough technologies or successes of big data. So one area which is often cited as very successful with big data is image processing, computer vision, like face detection, face recognition, image classification in general. I'm going to talk about that particular part a bit later. Speech recognition. I suppose you probably all remember when you tried to do speech to text 10 years ago, like 2005 or something. It really sucked. I mean, you had to be really lucky for your favorite electronic assistant to really understand your query. And I think 2011 or 12, I think 11 was actually a kind of breakthrough year on that, where deep neural networks were for the first time used with great success for speech recognition. And now if you use an Android phone with Google Now or an iPhone with Siri, usually it understands your query pretty well. Even the other day I was driving to the airport and was picking up my friend. So I just took my phone and I said, Google text, my friend, I'll pick you up in 20 minutes. And yep, sent a text message and everything was fine. And that simply wasn't possible 10 years ago. And then there are other applications like network security risk assessment, Similarly, spam filters, any other kind of text processing, if you think about translation, or recommendation systems on Amazon or Netflix, all these recommendations, it's all simply big data analysis. Trading signals for the finance market, and last but not least, medical diagnostics. And medical diagnostics and healthcare in general is actually a field which I think will tremendously benefit in the next couple of years from big data. So one example here is Google Flu Trends. 2011, there was a paper from Google about correlating search terms in Google search with the influenza virus outbreak. And so what they did is basically to look for certain terms, how often they were searched, basically as on Google Trends shown before. Symptoms of influenza or complications of influenza, like pneumonia, fever, or early signs of flu, etc., etc. And there was this large corpus of search terms which was used to correlate that with the actual influenza outbreak. There were two models that's why there are two columns. And as you can see here, the prediction, in hindsight, the correlation of the model with the real influenza outbreak is actually a really strong match. So in red, you see the influenza frequency, essentially, so the outbreak strength. And the dotted line is the model. The dashed line was the older model. That's where this other column here comes into play. But if you focus on the dotted line, you can see it really very well aligns with the actual flu data. And that's only in a few months in 2009. If you look at a few years time span, 6 years, you can basically directly see the spikes and the annual outbreaks in flu. You can even see these double spikes in point. Oh yeah, thanks. You can even see these double spikes here in this year, and then this year they are reduced. There are outliers, where it doesn't work, but overall the correlation is really high. And this, again, this was done in hindsight, but to validate the model. But it really works, and this is really tremendously powerful because you can immediately notice outbreaks or even predict them when they're on the onset, and then based on that you can perform targeted countermeasures like early vaccinations already, and long term you might be able to healthcare might be able to understand the dynamics of how an epidemic actually spreads, and maybe how countermeasures at larger scale can be done, maybe at hubs or airports or other hubs, for instance. And this is only a very small example. I think this is really just the beginning where big data can be used in healthcare and in medicine. Another example, which is I think way more powerful and promising, is when you look at the molecular level or at the cell biology level. So the human genome has about 3 billion base pairs. So in other words, you have your DNA contains basically the sequence AUG, ACG, blah blah blah, etc. And a triplet of those is a codon, and that encodes a protein, or an amino acid for a protein. And overall, we have about 3 billion base pairs, and you can basically encode them in 2 bits per base pair. So it's basically CD. If you put your genome on one CD, it's complete. It doesn't capture all cells, obviously. That would be way larger, but it's what basically your genetic blueprint. And that's not so much, if you think about it. But on the other hand, from a computer science perspective, 700 megabytes isn't really much, but every bit here really counts, and counts not only in terms of storage, but counts in terms of if something goes wrong with one bit here, then that could have tremendous or fatal consequences. So the way, just a brief repetition on molecular biology. The way this works is that the triplet of these base pairs encodes one amino acid, and then amino acids are synthesized into this long polymer chain, which is a nascent protein, and then in a process called protein folding, this chain actually develops structure, secondary structure like these helices, and then tertiary structure like the global 3D structure, and then you've got the final protein. And this shape of this protein is really critical for its function. So if the protein were misfolded, then it usually wouldn't be able to fulfill its function. In the best case, it wouldn't do anything. In the worst case, it might be fatal, or it might really cause serious diseases. And the sequence determines the structure, and the structure determines the function. So in other words, if there's anything wrong here in your DNA sequence, any transcription errors, any mutations, then that might cause maybe just a slightly wrong protein, and that will cause a slightly wrong structure, and that will cause your proteins not to function. And there are many diseases which actually go back to protein misfunctions and originally to DNA errors. So if we really want to understand the relation between the DNA sequence, your genome, and your health, or how much you're prone to diseases, for instance, that's why we really have a long way to go. Because from ab initio, first principles, it's virtually impossible, basically, to really complete the whole cycle and understand how this sequence determines whether you're prone to having, let's say, skin cancer. So that's where large-scale sequencing comes into play. And in 2001, there was a call out for, so basically among in the Human Genome Project, there was the call for the $1,000 genome. So genome sequencing for for the 2.9 billion base pairs was prohibitively expensive when the Human Genome Project started. And then in 2001, there was a price promised basically for any company which brings the price for one human genome to $1,000. In 2003, Human Genome completed, and as you can see here, the price for one genome sequencing is basically Moore's law until 2007. In 2007, there was a breakthrough, and there were new sequence technologies which completely changed everything, and you have many orders of magnitude decrease here. And now you can actually get your genome sequence for basically $1,000. There are companies, 23andMe and others, you might have heard of them, which really give you either a partial genome or really a full genome sequence for $1,000. And that is an incredible breakthrough, because that really allows us to apply big data analysis to genomics. And as I said earlier, it's virtually it's almost impossible to understand just from the DNA sequence what kind of disease you might develop based on that. Of course, you want to understand what's going on, but you're searching this endless pile of possibilities. And with big data, we can now collect genome sequences of a lot of participants, a lot of patients who might have serious diseases or very rare diseases, correlate the disease phenotype with the genome sequence, and then really see what are the correlations and what parts of the genome give rise to what diseases. And that can also be used in prenatal diagnostics to, for instance, early on, maybe just supplement whatever's missing, or etc. And even before that, you can determine whether you, as a potential parent, might be prone to having kids with any disorders, for instance.
But isn't this view a little bit too optimistic? Most genome-wide association studies don't come up with anything concrete.
Yes.
Even if you focus on the diseased populations, and with regards to whole genome sequencing, if you take even kids with genetic syndromes, you apply genetic sequencing, most of them you would not be able to tell what is the harmful variation.
I think, yes. I think that's completely right. That's the current state. But I think that's, in my view, that's a limitation of the limited amount of data we have. Because I mean, if we at some point have enough data, then you would assume that the noise basically cancels out and you really see the signals.
I think this is a view that is very optimistic.
It is.
Millions of dollars that have been invested in genome-wide association studies in various diseases, being able to detect only 2% of the variation and so on. And this is in very targeted surveys.
Yes,
so you target, so maybe you will have much more data, but the number of positive cases is not going to grow that much.
For the rare diseases, certainly not. Yeah, it might be a very
common diseases like schizophrenia, and so there's two ends of the spectrum. So in common diseases,
excuse me, can we postpone this? It's not a genomics session, I guess. So maybe we can discuss one later.
It's a good point. Maybe we can follow up later. Just to summarize it, I agree. It's an optimistic view, but I think there's reason to be optimistic. But we can follow up later. It's a good point. So the next area where big data is really extremely powerful already is for natural language processing or any other kind of text processing. So, for instance, there's this work from Chris Manning at Stanford, published last year, where they, the idea itself is, by the way, not new, to build an embedding for words in a vector space. And so they take a large corpus, text corpus, Wikipedia, for instance, and then simply, based on the core occurrence of words, build this embedding. And each word corresponds to one point in that vector space. And that vector space then has very interesting properties. So, for instance, if you look at nearest neighbors of, let's say, the term frog, then the closest points, the nearest neighbors in that vector space, are actually other frogs. Well, you've got the probel as first match, and then toad, makes sense, and then all kinds of frogs, which, aside from lizard, I suppose only a few people in this room, including myself, would have known actually frogs. So it's pretty cool. So the vector is basically gives you a measure for, or actually the Euclidean distance between these vectors gives you a measure for the semantic similarity, purely extracted from text harvesting. The second nice property of this vector space is that linear structures actually capture relationships between words. So if you take the word pair man and woman, for instance, and then you take the term king, then adding the vector which you found from man to woman, starting from king, gives you queen. And so here's just a subset of what they discovered in probably the first two eigenvectors of that space. You've all the male-female pairs here. You've got Sir, Madam, Heir, Heiress, Count, Duke, etc., etc. Same thing for companies and CEOs. You've got Verizon, McAdam, Vodafone, Color, etc. And adjectives. So you've got the normative, the comparative, and the superlative. And you can see this, the vectors between the different words are very similar, even in this two-dimensional representation. So that's a structure of the vector space embedding. So that's all coming from big data analysis. But as I said already in the beginning, in order for big data to be really useful, we need tools to extract and identify patterns and trends in the data. And one of the trends, which is really an extremely powerful tool and kind of also a buzzword nowadays, is deep learning. And deep learning, just very high level, it's an iterative learning process with multiple levels of abstraction, and it features nonlinear transformations in the model. And the probably most common deep learning architecture nowadays are convolutional neural networks, which are in their way also inspired by the visual cortex. So the idea is that you have neurons which trigger responses at the next level or layer of neurons if a certain activation threshold is reached, and each level increases the level of abstraction. So just a sketch here, how that looks. You've got the lowest layer, and the lowest layer, basically forwards information to the next layer, and then you might have some node in the network which actually encodes something like a diagonal line, so a feature. And then further up in the model, you might have something like a face node, which really triggers when you see a face, or a cat, for instance. And this is based on neural networks, and the story of neural networks is fairly long, fairly old. Just a very simplified history here. It started in the 40s already with a mathematical foundation. And in the 50s, neuroscientists were included in collaborations to really try to build neural network models which are inspired by how the brain is believed to work. In particular, the visual cortex of cats, I think, was used for analogies. And that was kind of a big thing back then. A lot of research money went into it. But then in the late 60s, there was a bit of a downer because Minsky and Papert published a book which pointed out previously unknown limitations to neural networks. And that fairly much froze the field for many years. And there was a lot of disappointment, and there was not so much research being invested in it anymore. And then in the 80s, there was the first renaissance of neural networks. There were successful applications, like Jan LeCun's work on handwritten digits recognition. So this was actually applied to zip codes in the US on regular envelopes. And the purpose or the goal was to recognize these digits as a neural network, which honestly, some of those I have trouble with. And they used this architecture, so it's 5 layers, 3 hidden layers. And they only used 7,000 training images. The images or the numbers were actually pre-segmented. So they worked on, so they trained single digits basically. That's why you have 10 output units on top. And it turned out to actually work fairly well. So they achieved a fairly low error rate. And that was back in 89. And that was a really good success. But then in the 90s, support vector machines came out, and those simply worked very well in practice. And support vector machines are, I think, probably one of the most used machine learning frameworks or classifiers in the 90s and in the 2000s. And now they're being replaced more and more by more modern architectures like neural networks again. But basically, there wasn't so much going on. There was the second downer, basically, a second ice age in neural networks. And then in 2006, there was a breakthrough again from Geoff Hinton, and a few other things were also going on, which caused the second renaissance of neural networks. In addition to these algorithmic advances, GPUs were becoming more available, which helps not only at inference time, but also at training time, but moreover also in actually iterating the model. Because if you build a model, then, I mean, there's a lot of alchemy involved, so you don't really know in the beginning how to build it. And so you need to iterate it until you really come up with a good model. So that's where processing power helps. And then, as I mentioned in the beginning, you have all these synergies or dependencies with other technologies which have just been emerging in the last decade at the scale which is required. And 2 fields, I think, where deep learning is really very powerful nowadays, very successful, is in computer vision and image processing. And as I mentioned earlier in the beginning already, in speech recognition. So again, if you talk to an Android phone nowadays, there's a neural network behind it, which actually translates the audio signal into an image and then applies basically image processing techniques, deep learning based, to extract what you actually were saying. And one particularly interesting challenge in image understanding is object detection and object classification. Arguably the 2 think, main ingredients to really understand the scene in addition to segmentation. And there's the ImageNet challenge, which many of you might have heard of, which is an annual challenge, an annual call for participation where new models can be evaluated and are competing to win in 2 categories. The first one is detection. So as you can see here, there's a bird, and the bird has a frog in the mouth, or the beak. Or here, a bit more complicated, there's a person holding a hammer, and there's a flower pot here also, and there's a power drill on the floor. Or even a bit more cluttered scene with, partial occlusions and everything. So that's a typical, I think that's from 2014, ImageNet challenge for detection. And then you have also the classification challenge, which features a couple of thousand categories. And the objectives there is for the classifier to understand, or basically to classify what object is shown. And these classes are often very similar, so this is actually really a pair of classes, Siberian Husky and Eskimo dog. Difficult to distinguish for a human, but this is one of the, these are 2 of the classes, the distinct classes in ImageNet. And in recent years, the ImageNet challenge has been really dominated by deep learning, convolutional neural networks. In 2012 in particular, there was a paper by Krzyzewski, Sutzkever, and Geoff Hinton. And they achieved a 15.3% error rate. So this is, it's accuracy, but it's actually error rate. And the second best was more than 10 percent points worse than that. And this was, I think, really one of the recent breakthroughs where people realized how strong deep neural networks are actually nowadays already for image understanding. So they're successful. And the features are learned automatically. They're not handcrafted anymore. That's a bit of a paradigm shift. If you worked on traditional computer vision and you're used to learning using SIFT features or Hawk or your favorite wavelets or something, then you feel you kind of understand what the system is trying to detect and what it's doing. But with deep learning, that's not the case anymore. So it's essentially a black box. And you don't really know what's going on inside. But the question is, do we really need to sacrifice our understanding of what's going on inside, or can we somehow infer what the model is actually learning and doing? And there has been a really great work, I think, by Matthew Zieler and Rob Fergus, published last year, visualizing and understanding convolutional networks. And what they did is they built a deconvolutional network which projected the feature activations back to the input pixel space. So they applied this on the ImageNet model, which won the classification challenge, which I just mentioned a few slides ago. And then for each layer here, they basically they redirected the output of the layer into their deconvolutional network to project it back into the previous until they reached the input layer, the input pixel space. And by that, they were able to visualize what's being learned on what layer. So the first layer here, I don't know if you can see this one on the projector, but very similar to here. It's basically, it's oriented edges. It's Gabor wavelets, essentially, and some color blobs. So it's not really very surprising, but the model learns what traditionally we were using for traditional classifiers. Kind of cool. The second layer gets a bit more abstract, so it learns also edges, but also corners and some round shapes already here. As you can see, these give rise to these activations. And then here, actually a nice example for edges. So it's one layer of additional abstraction. Then the third layer learns texture. Like, for instance, here, these web-like or structures are represented here. Text is identified. Already some kind of human upper torso outline is triggered on. And then on the fourth layer, you already get very class-specific parts of objects, like dog faces or bird feet, for instance. And notice here that the dog face is actually very exaggerated. So you really see clearly the features like the nose and the eyes and the tongue, but nothing else around it. It's mostly facial features, and it's actually, I think, transferable to these ones. And then on the fifth layer, you actually start to see entire objects like cars, flowers, bikes, keyboards, even in different poses here, and other things which look like keyboards but are not keyboards. And when you compare these dog features here, that's what I meant with exaggerated on the previous layer. These are a bit more global. I mean, they capture more of the whole dog. Versus here, you really see more the local features of what really defines the face. So you have this abstraction of features from one layer to the next. And based on these insights, the authors also were able to, first of all, they experimented with the network and took out several layers and to see how the performance would decrease. And they basically established that the, I think, 7-layer network they were using was kind of the minimum. They were able to, I think, to remove like one of the middle layers without significant performance drawbacks, but overall they found that 7 layers is really is key already for this complexity. And interestingly, they were also able to improve the original ImageNet model by 1.7 error percent points. So what they did is they basically just adjusted some parameters like I think the stride and the filter size on the first layer because they saw that the first layer in the original model had some aliasing artifacts and wasn't distinct enough or distinctive enough. And by changing that, they got a different first layer of features and came up with a performance improvement. Pretty cool work, I think. And this basically tells us that even though features are not handcrafted anymore, we can still make an effort to understand them. And understanding them helps us also to improve the model. And this brings me to the topic where what I've actually been working on with colleagues at Google. So we were trying to build a network to recognize business categories from images. So this is a paper which just came out at CVPR, Ontological Supervision for Fine-Grained Classification of Street Use Storefronts. And the idea is that we want to improve maps. So I work in Street View on computer vision, and one of the things we're doing is to ensure privacy rules are upheld. So the whole face blurring and license plate blurring, etc. That's nowadays all done with deep neural networks. So that's something we do. But in addition to that, we also try to find useful information for mapping purposes in Street View, like house numbers or navigation signs or stop signs, etc. And this project takes it a bit further on the abstraction level, basically. So we want to know what is a category of a business photo so that we can serve queries like coffee shops near me. That brings us back again to the ecosystem. I mean, nowadays when you're walking along with your cell phone, you actually want these queries to work, and something like coffee shops near me. And that eventually shall help improve maps. So example images which we're using are shown here. So this is a bank, Capital One Bank in America, and it's a finance institution and it's a bank. Another example, food and drink, cafe for this bakery. pizzeria, fast food, kind of hole in the wall, and some shopping store. I don't even know how we would fine-grain describe it. Something like hardware maybe, but it's heating supplies. And I would say traditional approach would be that you run OCR on these images and you find whatever text you can detect and transcribe. So in this case, for instance, ideally you could find the grain, which is the name of the cafe. You would find cafe bakery, which is awesome because it already gives us a category. And bread, cakes, coffee, which again is great because it gives you an idea of what you can actually buy there. Coffee in addition to bakery goods, for instance. And then you could do something like a bag of words approach or some natural language processing, etc., to infer the category.
Do you use Tesseract for OCR recognition?
Excellent point. Not anymore. Because Tesseract is great for books. I mean, right? That's what it was developed for. But it's really not that great in the wild. With distortions, mostly distortions actually. So our challenge was actually that we wanted to do it without OCR. For multiple reasons. A, OCR simply isn't really perfect yet. It has made tremendous advances in the last couple of years, I would say. Again, also with deep neural networks, both on the detection as well as on the transcription side. But there are still OCR problems. Even if OCR would work perfectly, there are sometimes occlusions. It might be a tree or a pedestrian or something. And if you're going to only half of the word restaurant, it might confuse you. Then secondly, we want to be language agnostic. So if you are in Chinatown or in general in any area in the world where there's non-Latin script, or let's say not even English, as a language, then it's tougher because our OCR, again, doesn't really work there yet. And third, there are businesses which don't have text. Either it's occluded or they simply have a logo. I mean, logos are actually fairly easy to detect, but some businesses simply don't have much visible text on the storefront. So if you look at these examples, it's actually pretty damn hard to infer what these businesses are. I'm biased now, but I mean, you can make your own guesses. So we've just blocked out the main text here. I would probably have guessed, yeah, this might be some cafe. This maybe as well, maybe closed. This, I don't know. And this, I don't know, 99 cents, maybe some kind of $1 shop. I don't know. That's what I probably would have guessed. If you look at the text, then, yep, this is food and drinks. This is actually a shop which is selling benches for food and drink shop. So it's actually really mean, but that's one example we came across. And then this is a cafe I would have not known. And this is also food and drinks. I don't know what they sell for $1, but it's a pizza place. So it's hard. We tried it because it's hard. I don't know. And what we use is the inception model, or the so-called GoogleNet, Deep Convolutional Network Architecture, which was used in the ImageNet challenge in 2014. So it's a very deep neural network. Paper of the title was Going Deeper with Convolutions. And so it was pre-trained on the ImageNet data. And then we trained the top layer with 1.2 million training examples of here's an image, and these are the category labels. And we used 2,000 categories in a hierarchy under top 7 categories. And the top 7 were entertainment and recreation, health and beauty, lodging, etc. And these 2,000 categories are basically what you also find in Google Map Maker. So if you want to create a business on a map, you can select the category, and there's this whole ontology of categories. That's what we used. Here's an example of one part of that ontology. So a pizza restaurant has the upper category of restaurant or cafe, food and drink. In this particular case, a pizza restaurant could also be classified as a takeaway restaurant or a fast food restaurant. So we allowed multiple labels per image. And the distribution of categories was fairly unbalanced. We had a lot of shopping, a lot of auto repair and auto stuff, and only very few, eye care, nightclub, etc. So we had a very strong head and a large long tail. The results are pretty impressive though. So the scores here are the confidence scores, and shown are the first 5 predictions from the model. And you can see here for the dental clinic, it says health and beauty with 99% confidence, health with 98%, doctor, and still with 95% confidence. Sorry, that's a dentist. Here there's McDonald's, correctly classified as fast food and everything above. Here we have a church, which is an interesting example because it's very, I wouldn't know, I mean a Christian church, you could define, it has a cross or something, but I wouldn't really know how to actually characterize or describe in words how would you recognize a church. And then on the lower end, I mean, we also have 3 education culture. It's in the eye of the beholder, but essentially misclassification, which didn't belong to the ontology here, but with a very low confidence score. So they're just included because we just listed the top 5. More results, gas station, pretty well recognized. Then here we have a butcher shop. And again, you obviously can see that the higher level or more general category is usually predicted with higher confidence than the finer grained one. Then here we have a bike shop, which is classified as sporting goods, etc., etc. You have laundromats. This was actually a surprise because we had only, I don't remember the number, maybe 5,000 or something laundromats actually in the training set, but it does fairly well on laundries. Surprising. I don't know if you can see it, Starbucks, 100% confidence that Starbucks.
Are those completely random examples?
Yeah. I mean, we had in the paper we had, I don't know, 50 random examples or something, and I just picked 15 out of those, but almost random out of random. I basically just deduped that we don't have 2 Starbucks here or something. In the interest of time, maybe I don't discuss the curve here in long detail, but essentially this is just the precision recall curve for all of these categories. And these are the top categories. So where the model was most certain is, oops, it's cropped here. Anyway, it's food and drinks at 61% precision at 76% recall. Then finance, 59% precision at 84% recall. Gas stations, an amazing 96% precision at 92% recall. And then etc. Here you can see the numbers for automotive, laundry, again, surprising, and beauty. It's cool. We also compared the performance of this model with the original ImageNet model from 2012. And you can see that the 2014 model, which we used, performs much better in essentially in all categories than the 2012 model. And then we also compared the human accuracy. So what we did is we did 2 studies. The first, we sent 75,000 images to 2 operators and figured out or checked if they actually agree on a category. And in only 69% they actually agreed on the category, which is pretty much the order of magnitude where our model predicts, actually. In the second study, we had 20,000 images and sent them to 4 operators, and then averaged the agreement, and here we got to 78% agreement, which is still pretty much the performance level we gained for many categories already. So then we did this experiment to see what's going on there. Has the model actually really ignored text, or maybe it was cheating and actually trying to read or something? So we removed the descriptive text from the images. So here auto, we just blurted out. Nails, remove the nails, and send these images back into the model to see what's actually happening. So here we removed auto, and yep, it's still classifying it correctly as gas and automotive. Also as shopping, also as store. The 5th one, vehicle dealer, is actually not present here anymore. So it lost, that's a vehicle dealer, but it says transportation now. Okay. But now, if we go to dental, then removing the text actually really screwed up the prediction. It still figures out that it's a health and beauty, in particular beauty. But then the third, cosmetics, is already wrong, and it's much lower confidence. And the fifth prediction is actually that it's a hair care and not a dental place. So it really learned to, apparently, to read dental. Next example, a wine and liquor store. Previously well recognized, now it's really confused. It still figures out beverages as a fifth highest label, but in between it says maybe a restaurant, which is not completely wrong. It doesn't say it's a laundry or gas station, but it's you can clearly see there's really a lot of signal in this wines and liquors. And think of it, I mean, wines and liquors is not a very descriptive thing. It's not a Shell logo, it's not a Starbucks logo or something which is easy to learn. It's a very specific thing for a beverage store. Nails spa, sorry. So same thing, it actually thought instead of a nail salon with 94%, 95% confidence, it thought maybe it's a hair salon. It's not that bad. It actually still figured out it's a beauty salon, but with lower confidence. So it did learn to read. It cheated. And then we did the inverse experiment. So we simply took an empty image and wrote pharmacy on it. I kid you not. Just these 8 letters on a white image. And yeah, and the model was pretty sure it's a pharmacy. So yeah, I learned to read. So the summary of this is our model was performing at human level accuracy to categorize businesses for most classes, and it learned to read at least some labels. And both I think is pretty cool. It's very fascinating. In particular, when you think about that this is a very complex task and kind of ill-defined. When you think about how would you define the characteristics of a church to explain someone how a church looks like, or laundry or something, it's fairly, fairly difficult, I think, to explain and understand for a human what's going on. So in that sense, taking a step back again, in a way, I think this already starts to transcend our understanding and in performance-wise, maybe even our limits. In a way. And with that, I actually like to end with a quote which I found recently, which I found very interesting. I just put it out here from Danny Hillis, an entrepreneur and engineer. He said, "We will not engineer an artificial intelligence, rather we will set up the right conditions under which an intelligence can emerge. The greatest achievement of our technology may well be the creation of tools that allow us to go beyond engineering, that allows us to create more than we can understand." And that is where I think I could see the future of be it deep neural networks or in general machine learning as a field. Yeah, and with that I'd like to close and take questions.
So you use the Google Linet transfer learning and use the pictures of the business. Is there any trick you used at Google to tune the hyperparameters, or did you just use the standard training?
It's a good question. I would need to check that back in the paper because we actually did that last year already. We might have tweaked the learning parameters a bit, but the model is unmodified.
And the second question would be, you introduced the paper of understanding convolutions from Matthew.
Yeah.
And would it be also an possibility to use that technology to improve your model? So like
certainly, I would. Yes, I mean, who knows? Maybe they're already working on it. I mean, we just published our CVPR paper last week, and that could totally be. Okay. In particular, I would be curious to see the laundry and the pharmacy actually somewhere in there.
Yeah. Okay.
Yeah.
To use this now, do you have thought about segmentation of Google Street View images to find out where the shops are?
Yes. Stay tuned for a new paper coming out hopefully soon.
Yeah, so you mentioned GPUs as one of the drivers for computational power. How does Google make use of GPUs in that sense?
It's something I can't talk about. Can't comment on that. I mean, but I think it's fairly obvious that GPUs are powerful, right? Yeah.
Yeah. So what's all about entities? What is it about relationship learning or behavior learning? Yeah.
Excellent question. I recently saw a talk at Stanford from Leonard Gebers, who used neural network, deep learning, to understand relationships between objects, not only spatial relationships, but also activity or action relationships. I can't summarize it within a few seconds, but that was very interesting. I think they published it last year. I think that's a very interesting read-up. They also came up with a kind of Platonian model. So the model learned like what an ideal cow would be, for instance, and then they were able to transform the differences of any cow instance from the ideal cow into post-estimation and everything. Pretty interesting stuff.
And you mentioned this idea of the mechanical Turk, yeah? So
yes.
Setting up, as you said, now setting up an environment where the machine observes the human. Is that are there similar works ongoing or at Google?
Yeah, I mean we have in-house operators to generate training data. It's kind of similar to mechanical Turk, I would say, but the concept's pretty much the same. You just have operators, volunteers, whatever, to generate large amounts of training data.
For example, behavior, people.
Oh, you mean
you get mails, Google Mail. And what do people do with the mails they receive? Do they forward them?
Oh, I see.
So
I see. I thought you meant specifically training.
We already have wikis.
I think that is. I'm actually not really entirely sure how that is used, but I think if you think about, I actually don't know if it's used, but I could imagine something like, if you get an email and you immediately trash it, could be used as a signal, I guess, that it's it is spam or unwanted, or maybe in general user interface feedback, right? If you if some user always clicks that button and then another button and then another button in the 5th menu layer or something, maybe it would make sense to put that as a first level interface button or something. So I think there are user interface studies for that, and maybe also some spam filter stuff, but I wouldn't know about something specific at Google.
So, next question, please, and the coffee break.
Right.
We have another talk.
Right. Thank you.